Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to finish up our conversation about precipitation by looking at how we can apply our knowledge of solubilities to separate out chemical compounds. So we've mostly been talking about some more general uses of solubility reactions. One of the very practical uses, and we've actually seen this in lab, is you can use two different compounds' sensitivity or preference to forming a solid with a specific ion to separate out multiple ionic species. So for example, both aluminum and magnesium want to coordinate to hydroxide. And what we can do is use their differences in their solubilities to figure out which one wants to coordinate with hydroxide more. And again, ignoring stoichiometry and just looking at the KSPs, you'll note that aluminum has a much lower KSP, meaning that it wants to be a solid a lot more than does magnesium. And so as a result, we should expect aluminum to form a precipitate at much lower hydroxide concentrations. It's going to take a lot less hydroxide to hit that critical limit to form a solid. And so as a result, we should expect aluminum to form precipitate first as I start adding in hydroxide. And so what we can do is try and figure out what sort of levels of hydroxide would be required for a precipitate to form if I was going to mix a solution of 0.1 molar aluminum and 0.1 molar magnesium. So how much hydroxide would be required to make the aluminum precipitate and how much to make the magnesium precipitate. So for the aluminum hydroxide, we can go ahead and set up the KSP equals the aluminum concentration times the hydroxide, essentially Q. Then we can go ahead and solve for the hydroxide concentration because we know what the aluminum concentration should be, and we know what the KSP is. And so the hydroxide concentration required would be about 2.4 times 10 to the negative 11th. Okay, that doesn't mean a lot, but it means that any hydroxide concentration above that level will form a precipitate. And that's actually a fairly low number. So we can turn that OH into a POH, that's 10.6, or a pH of about 3.4. So in other words, solid aluminum hydroxide will form at any pH above 3.4. So as soon as the pH gets anything above 3.4, which is actually quite acidic, we're going to start forming more aluminum hydroxide. The more hydroxide I add, the more aluminum will precipitate out. And you can essentially figure out what the aluminum concentration is at any hydroxide concentration using the techniques we already showed for buffers. Now, what would end up happening for that magnesium system? At what pH will it start to precipitate out? So we can again set up something very similar, then solve for the hydroxide concentration using a magnesium concentration of 0.1. And we find that it takes a concentration of 7.5 times 10 to the negative 6 molar or greater for the magnesium hydroxide to precipitate. Okay, let's go ahead and turn that into a POH. 5, that makes a little bit more sense, or a pH of about 9. I can work with 9. So this means that solid magnesium hydroxide will essentially form at any pH above about 9, which is actually fairly basic. So if we go ahead and compare these values, I know that aluminum hydroxide will form at pHs above about 3. Magnesium hydroxide will form at pHs above 9. So if I only want aluminum hydroxide, what we can do is set the pH somewhere in between about 4 and 8, let the aluminum precipitate out, and leave the magnesium in solution. And if you think back to our precipitation lab at the beginning of the semester, you might remember that's exactly what we did. We started with an acidic solution of aluminum hydroxide, and then we went ahead and made it basic. So we changed the pH to about 7. So actually we made it neutral. And we got the aluminum hydroxide to separate out. We pulled out the solid, and then we took the remaining liquid, and then we made it basic. So we brought the pH above 9 and collected the magnesium hydroxide. And it turns out you can use very similar techniques based on chloride concentration to separate out silver, lead, and mercury, which we did, or for various halide precipitates by changing the silver concentration to separate out silver chloride versus silver iodide, which we also did. So this is quite a nice practical technique you can use to apply your new knowledge about solubilities. However, next time we're going to dive in a little bit more about the formation of complex ions. So how you can go ahead and take something like aluminum hydroxide and make it dissolve by forming a new complex. Next up, aluminum tetrahydroxide. Until then, take care.